Albert Einstein's tensor equation for general relativity remains an incredibly accurate macroscopic rule, mapping how massive objects interact with the universe at large scales. But its predictive power relies on a rendered layer of reality. The equations work, provided you assume that space, time, and matter already exist as distinct given entities. We usually visualize this rendered layer as a heavy ball resting on a pliable surface. But if space and time are emergent properties of a deeper system, there is no passive container waiting to be bent by mass. This leaves a mechanical void. If a planet is not physically pushing down on a pre-existing spatial geometry, we have to explain the exact mechanism causing the distortion we experience as curvature. The phrase mass-curved spacetime is an effective summary, but it operates as the visible shadow of an unmapped underlying structural mechanism. The Relational Accessibility Framework, or RAF, provides that mechanism by starting from a single premise. Reality is a discrete network of allowed connections. In this framework, a stable pattern, whether it is a planet or a subatomic particle, is a persistent closure. It is a highly organized, self-maintaining cluster of connections. This intense, tightly bound closure mathematically forces the surrounding network paths to alter their routing, shifting local connection density to accommodate its rigid structure. Curvature is simply the mathematical mapping of this non-uniform accessibility across the network. Curved space is not a physical substance reacting to weight. It is the unavoidable visual rendering of a network structurally forced to redistribute its connection paths. To understand why the network redistributes, we must look at the rule governing every connection. The entire network constantly acts to minimize relational frustration. This diagram illustrates frustration mathematically. It is the phase mismatch between connected nodes trying to align their internal states. When these vectors conflict, frustration spikes. Left alone, the nodes shift their states into a phase-locked alignment, resolving the mismatch and lowering the systemic frustration. A massive object, a persistent closure, is a localized domain where internal frustration is extremely low and internal coherence is incredibly high. Because this closure is strictly aligned and coherent, it acts as a rigid structural boundary. It cannot yield to the surrounding network without destroying its own stability. To keep the total systemic frustration low, the looser, less rigid relations on the outside are mathematically forced to rearrange themselves around the unyielding closure. Gravity and spatial distortion begin here. The relational field must continuously warp and redistribute itself purely to prevent a catastrophic spike in frustration against a rigid object. We now have a distorted network of mathematical connections. The question is how that abstract topology translates into the physical distances we actually measure. This equation defines geometric distance as the inverse log of relational accessibility. As connection density between points drops, visual distance stretches. As dense closure changes the accessibility pattern, perceived spatial geometry automatically morphs to match. Time follows a parallel rule. In RAF, proper time is the accumulated computational cost of internal resequencing, the sequential updating of states within a closure. Near a strong closure, the surrounding network is placed under a heavier relational load. This increases the computational cost of local resequencing, effectively limiting how many internal updates a system can process. Time dilation is not the bending of a temporal dimension. It is simply the record of internal updates struggling to process under the extreme relational load imposed by a nearby massive structure. If space is a map of accessibility, we must account for why objects reliably fall toward massive planets without a pulling force. Here, we see a small test closure positioned near a massive body. The gradient vector field visualizes the local frustration cost, showing that the zone of lowest mismatch points directly toward the massive center. The test object moves closer to the massive body because migrating into an aligned phase region is the path of least mathematical resistance. As the massive body's influence radiates outward through the network, it distributes its closure across a growing surface area. The inverse square law is an unavoidable geometric result of conserving that closure influence over an expanding, uniform surface. Gravitational attraction is an emergent illusion. Smaller structures simply flow toward regions of lower conflict, governed by basic geometric conservation. This framework redefines extreme cosmic phenomena. A black hole is not an infinitely dense singularity of matter, it is a maximal closure fixed point. Inside this maximal closure, the internal gradient of frustration is driven exactly to zero. In an extreme zero gradient state, any physical asymmetry instantly introduces irregular gradients. Jagged spikes of frustration erupt, forcing the structure to snap into a perfectly smooth, symmetrical sphere. To survive without self-destructing from internal mismatch, the massive network structure must adopt perfectly spherical geometry. Black holes, planets, and stars are not spheres because gravity crushes their matter. Radial symmetry is the only mathematically stable way a massive closure can exist. RAF generates a specific prediction that diverges from standard physics. Gravity is not sourced by mass alone. We are looking at two bodies with identical bulk mass, but an X-ray view reveals their internal organization dictates their gravitational output. One features randomized routing, the other relies on ordered, phase-locked loops. The highly organized, phase-locked mass generates a different effective gravitational source profile than the chaotic mass. A lower frustration internal architecture allows the system to act as a deeper, more stubborn persistence basin, heavily modifying the relation field around it. Identical amounts of matter can literally warp spacetime differently depending on their internal topological coherence. Because network closure precedes visible geometry, the underlying network will show signs of failure before physical collapse occurs. Prior to a macroscopic structural breakdown, a system will exhibit specific measurable spikes in phase mismatch. We can observe this in astrophysics. A black hole accretion disk will broadcast topological distress signals before its visible orbital geometry fails, its flow violently fracturing as internal frustration spikes. Because every structure, from atoms to organic cells, is a persistent closure, biological tissue failure and material shear stress are identically governed by this rule. They appear as local topological decoupling before any chemical or physical drift is visible. Across all scales of nature, catastrophic collapse is always preceded by a universal warning sign, an invisible spike in relational frustration. This provides a specific solution for the barrier of high-velocity transport, applying to superconducting materials and advanced neural pathways. This is the RAF limit rule. A system's internal resequencing, the update rate we defined earlier, has a finite capacity. If the relational load from extreme motion or data flow exceeds this capacity, the closure begins to dissolve. Pushing past this limit requires engineering precise phase lock to protect the closure, rather than simply supplying the system with more brute force and energy. The next steps in applied science require a shiftomic particles toward measuring hidden network support and shaping attractor states. Reality is a mathematical competition for persistence. Mastering the architecture of closure gives us the exact blueprints to engineer the fabric of the universe.